Unit 2 is on the descriptive statistics and probabilities. Section 3.1 is on measures of center. Measure of center. This is the value at the center or middle of the data set. And what that means is based upon the specific center we are referring to. But the mean, or arithmetic mean, or average, might be another way to say it, is where we add all the data values and divide by the total number of data values. Sample means drawn from the same population tend to vary less than the other measures of center. That means, and that's based upon the fact that the mean uses every data value, or every data value in the sample. The disadvantage to using the mean, however, is that just one extreme outlier can change the mean substantially. It is not a specific property referred to as resistant. It's not a resistant measurement. What does resistant mean, you may be wondering? That's the presence of outliers does not change the statistic very much. So as a formula, we could look at the mean or average as the sum of all the data values, divided by the total number of data values, or the sample size. And the mean of a sample is denoted by x bar, so x with a bar on top, or the population of a population is denoted by this Greek symbol that kind of looks like a U that is pronounced as mu. Again, it's Greek. An example from the dataset body 1 biodata dataset measures the pulse rates. We want to find the mean of the first 5 pulse rates for males from that dataset. So 84, 74, 50, 60, and 52. All in beats per minute. We add all those up, divide by 5, and we get 64.0 beats per minute. The median, a second measure of central tendency. This is the measure of the center that's in the middle value when the original data values are arranged in order of increasing magnitude or decreasing magnitude. The order of that technically does not matter per se. It could be increasing or decreasing. Typically, we're taught increasing. It's typically denoted, well, I shouldn't say typically. There's no set way of denoting the median. You could write x tilde, so an x with a tilde on top, a capital M, the word med, the word median, anything like that. It does not change by large amounts when we include outliers, so the median is indeed resistant, and that's due to the fact that we do not use every data value directly, just the one that's in the supposed middle of the data set. If the number of data values is odd, though, the median is the mean of the two middle numbers. So, for example, let's say we have the numbers 1, 2, and 3. Right? The middle of that data set is the number 2, since it lies in the direct middle of that particular set. Likewise, if the number of data values is even, if it's even, then the median is the mean of the two middle numbers. So, for example, let's say we have the numbers 1, 2, 3, and 4. Right? So then, the median of that, we would take the mean of 2 and 3, since 2 and 3 both lie in the middle of the data set. And the mean of 2 and 3 is 2.5. For example. As a concrete example, let's find the median of the first 5 pulse rates for males from example 1. So writing that data set in order, we have 50, 52, 60, 74, and 84. The exact middle of the data set is the 60. So the median is 60.0 beats per minute. The median of these pulse rates, now with the 62 in there, when we wrote that in order, the median would be between 60 and 62. Add those up, divide by 2, we get 61. So 61.0 beats per minute. The mode, this is the value or values that occurs with the greatest frequency. It's the only measure of center for qualitative data. You could have no mode, or one mode, or multiple modes. A dataset with two greatest frequencies is bimodal. A dataset with more than two greatest frequencies is multimodal, but by that point you're starting to lose the center because it's not a typical data value. A dataset with no mode is where no data value is repeated, and one mode is called unimodal. If we want the example of a mode pulse rate from these pulse rates of 58, 58, 58, 58, 60, 60, 62, and 64. 58 is the one that's repeated the most often at 4 times, so 58 beats per minute. The mid-range measure of sound that the value midway between the maximum and minimum values in the dataset. So mid-range, we take the maximum plus the minimum and divide that by 2. It is not resistant since both the maximum and the minimum deal with the outliers. And it's very easy to compute, as you can see. It is different than the median, however, and it should also be noted that SAS is unable to calculate this directly for us. We would have to actually type in a formula to try to get it. Just to point out. But let's say, for example, we want to find the mid-range of these 5 pulse rates for males from example 1. So 84, 74, 50, 60, and 52. Maximum is 84, minimum is 50. The mid-range takes the mean of those two values and gets 67.0 beats per minute. The usual convention with rounding, and you probably saw it in the examples, the mean, median, and mid-range are rounded to one more decimal place than is present in the original set of values. The mode, however, is not rounded, because the mode just looks at the data set and just decides what's the highest frequency. You would typically, well, I shouldn't say typically, you should always leave all rounding until the end. So then that way, it doesn't cause errors with intermediate calculations. If we want to see if a mean or median are meaningful in these following scenarios. Zip codes of the hospitals in the United States. Well, a zip code is just a location. What's a mean zip code or a median zip code? Makes no sense. So no, it is not meaningful. A telephone numbers of everyone in Waterbury, Connecticut. It doesn't really particularly matter where. A telephone number is, again, it's just a way of location, right? Since it has that area code at the beginning, and then it has the various other numbers to pinpoint the exact location of who you want to call. So because of that, the mean telephone number or median telephone number doesn't really exist. So no, it makes no sense. How about the prices of all pairs of sandals in a department store? Right, you can have the mean price of a pair of sandals to know what the average price is of a pair at a particular store, or you could have the median when you're especially at ones where the prices fluctuate a lot from a cheap basic pair between a high-end designer pair, for example. So yes, mean and median are meaningful for that particular one, although the mean is probably slightly more meaningful, but that's not what we're asking in this. The mean of a frequency distribution. This is the same idea as the mean of a dataset. The formula is that we take the sum of each frequency times the midpoint of each of the classes, divided by the sum of all the frequencies, which should be n. I say should. Depends what you actually have in the table. But for example, that's the first 2 columns of this frequency distribution down here summarize the pulse rates from males in dataset 1 body data. We want to use the frequency distribution in the first 2 columns to find the mean. So here we first have the class midpoints of each of these classes. How do we do that? We find the mean of each of these classes. So add up the two bounds, divide by 2. So such as in this case, the first one is 47 as the class midpoint. And when we take each frequency, if we take the frequency times that midpoint, we obtain this last column, so 705 for example. If we add all of those frequencies times the class midpoint, we get this value down here of 10,611. And the sum of all the frequencies, so add this column, 153. So 10,611 divided by 153 is 69.4 beats per minute. The weighted mean. This is when x data values are assigned different weights, W. The weighted mean takes the sum of each weight times the associated data value divided by the average of the sum of all the weights. Right? So the weighted mean takes the sum of each weight times the associated data value divided by the sum of the weights. So for example, let's say in her first semester of college, a student of one of the authors took 5 courses. Her final grades, along with the number of credits for each course, were: in one class she got an A for a 3-credit class. She got a second A in a 4-credit class. She got a B in a 3-credit class, a C in a 3-credit class, and an F in a 1-credit class. This grading system assigns quality points to lower grades, as do most universities. A is 4, B is 3, C is 2, and D is 1, and F is 0. We want to compute her grade point average. So X are the grades, W is the weights of the credits. So the sum of each grade times the associated weight, so 4 times 3 plus 4 times 4 plus 3 times 3 plus 2 times 3 plus 0 times 1. Divided by the sum of all the weights, so 3 plus 4 plus 3 plus 3 plus 1. This makes 43 over 14, or rounded to 2 decimal points, 3.07. Thank you.